Well, good morning, everybody. This first session on the beginning of the conference of electrical engineering in 2017. Well, due to some technical issues, the first conference was not able to be connected, to be presented. Then we have our second presentation. This talk has the title that Hexapodopter, astronomical hexapod. The talk is given by Soto Guerrero, and he's a collaborator of Guerrero. Okay. Well, as you already mentioned, the title of my work is Hexapodopter, astronomical flying hexapod. The agenda for this presentation is as follows. I will start by giving an introduction, and then I will describe the mathematical model for the vehicle, and again I will show some simulation results that we proved successful. And well, the Hexapodopter is a novel configuration of a flying vehicle. It has 6 propellers as a normal hexacopter, but if the six propellers are mounted on 6 links that can be articulated and reconfigured during flight, and it makes the vehicle a multimodal vehicle. It can fly and also walk as a normal hexapod on land. Right? This is a rendering of the vehicle. And from what we have seen on the state of the art, there are many vehicles, many different approaches to these designs. We classified all those designs in static and dynamic arrangements. The static arrangements are fixed. Once they build the vehicle, they cannot change the orientation of the propellers. And the dynamic arrangements, they have several degrees of freedom that make possible to change the direction of each thrust force generated by the propellers. On this graphic, I show you a multicopter with 4 propellers. On each propeller, it is possible to change the orientation of the thrust force on the axial axis and the perpendicular axis. So there we have a propeller with 4 angular velocities for the propeller, and in total 8 servo motors to change the orientation of the propeller. So this is a dynamic arrangement, and there are several approaches to control this vehicle. The one we followed is we model the vehicle as a normal hexapod, but this time each link has 3 degrees of freedom. It has what we call a swing axis, a lift axis, and a knee axis. So each link has 3 degrees of freedom, and as you can see, the thrust motor, the brushless motor, is mounted over the femur of the link. So it is possible to change the orientation of the thrust force with respect to the center of mass of the vehicle. What I just told you, we modeled the physical configuration of the vehicle following and using normal vector computation. And this is what I will now introduce, the mathematical model that we formulated with this vehicle. So here is a very simple model to see how the vehicle performs. First, we have the vector given by the angular velocities of each propeller, of each motor. Then the transition matrix, and from the product of the two, we get a vector with the force and torque exerted around the center of mass of the vehicle. Here I show you with the letter D, the reference strength where the center of mass is located. Right? And the transition matrix is given by 6 different vectors. Each vector is given by the configuration of each link. As I told you, each link can be reconfigured, and during flight, we can change the value for each of these. And from each vector, we formulated this equation with a normal vector and the cross product, as we normally do when we compute torque. Right? So the total range over the center of mass is given by the angular velocity multiplied by this factor, and the transition matrix. What we did differently is we used this model to verify the holonomic capacity, the holonomic capability of the vehicle by studying something called force closure. Force closure is a concept used in robotics when someone tried to study how well a group of forces grasp a rigid body. If a set of forces grasp the body correctly, we say that it's a force closure grasp if it can counteract any force or torque. Suppose I grasp it this way the mouse, I can push it in this direction, and it is force closure because it is in equilibrium. But if I push it this way, it might fall, right? So the next level on this concept is force closure. When I grasp very firmly the mouse, and no matter where I push it, it will remain in equilibrium. So we use this concept to study the capability of a rearrangement of the rod by finding that the graph matrix that defines the forces being applied to the rod being equivalent to the transition matrix I just showed you. So given this similarity, we formulated the form closure applied to the Hexapodopter. And as you can see, it has a very formal way to define that a grasp over a rigid body is form closure. The first is that it has to be in equilibrium, right? The second is that the forces have to be all positive. So if we make sure that this graph matrix satisfies this problem, this linear problem, we guarantee that the graph is form closure. We did the same for the Hexapodopter, adding a fourth constraint. We added the weight of the vehicle as a grasp force for the rigid body, and under this constraint, we tested the forces applied to the rigid body of the vehicle. It is a form closure arrangement, right? So if it is a form closure arrangement, we can exert a force or torque around the center of mass of the vehicle in any direction. Under that situation, under that assumption, the vehicle can move on each direction without tilting, as a normal vehicle does. Right? A normal vehicle has to tilt first, gain horizontal acceleration, it tilts backwards to decelerate and brake, and then forward again. And this problem is we have to maximize D, which is the minimum force that have to be applied to the rigid body, so we can generate any range around the body. So we plotted which is the minimum force D that we require to exert on the rigid body for different angles on the lift degree of freedom that I showed you at the beginning. And we also use the mathematical model to depending on which is the lift angle, maximize the accelerations around the x and y axis. So as you can see, by increasing the angle of the lift degree of freedom, we also require a greater force, a minimum. The D, it increases when the lift angle increases, and also the maximum acceleration also increases. So we chose a configuration for the vehicle which could help us to increase the maximum acceleration over the x and y axis, and we propose a trade-off between the maximum force that every motor can exert and the margin that we have to counteract any force by just accelerating or decelerating the thrust force of the motor. The maximum, the best performance we get is around the shaded area. So we use this value, the 40 degrees of leaning, to reconfigure the robot and test it on a flight simulation. Right? So this is how we modeled or how we designed the control architecture for this vehicle, and we made it describe a limit speed trajectory. What is different from the other approaches is that the translational and rotational dynamics can be decoupled because the point closure characteristic of the vehicle, we can control the translational and rotational dynamics independently. Right? This is a simple simulation of the vehicle. As you can see, this is the mission plan. It took off here, and then fly above the ground level or 1.5 meters above ground level, and then describe the landing escape to land just before it completed the landing escape trajectory. From the angular velocities, we see that they are visible and they are all positive, which means that we can indeed make this robot in real life. Here I show also the altitude during the whole flight. Here we see that it took off, then it followed the landing escape trajectory and at the end it landed. And here I show you the Euler angles for the roll and pitch angles. As you can see, they are all approximately 0, which means that this robot took off, described the landing escape, and landed without leaning to one side. It always remained perfectly level. It remained horizontally and perpendicular to the ground, to the XY plane. And the same happens for the angle. It always remains pointing in the direction it started. Right. So that's it. The conclusion is we presented on this paper a hybrid novel robotic platform that is called Hexapodopter that we are planning on building it. We prove mathematically that the reorientation of every thrust force makes the vehicle holonomic in the translational movement. We found that the best trade-off between maximum acceleration on the XY plane and the form closure quality, which is given by the G parameter which I mentioned. Because the locomotion of the Hexapodopter has been proven successful before, here I showed you a set. We can conclude that the synergy of the two robotic platforms increased the flight performance of the Hexapodopter without interfering with its ability to perform direct locomotion. That's it. Okay. Thank you.
Well, we thank the and we have time for some questions. Any question? No? Well, I have one. Can you show the plots from the raw angle? Yes. Well, I am confused because on the red one is like around 1.5 radians, and then you have one below that you pointed out that is almost zero, meaning that there's no tilting on the body.
Sorry, there's a mistake. I'm really sorry. Read the altitude. The altitude.
Okay, so it's
restricted. Yeah, it's moving outside. The up and right direction.
Yeah,
my mistake.
Okay. Then another question. Can you put the plot of the figure of your Hexapodopter?
Right. I think it is. This one?
Yeah, no, the one before.
The render?
Yes. Okay, that or the other one. So in a usual configuration for a quad helicopter, the idea is that the degrees of freedom of the equator are fixed with respect to the body.
That's right.
So in this case, because this one can work at the same time, the idea is that you can orientate somehow the equator as well.
The idea is that we can make this robot take the configuration of a standard vehicle with all axes of the motors being parallel. But we can also change the orientation of the motors before flight, and then once it reaches the 40 degrees that I showed you, it can pick up and perform holonomic flight.
And when you are flying, you want to keep it always horizontal, the body of the helicopter.
Right.
In that moment, all the actuators are parallel in the actuation axis, or it's like you are using maybe 4 for flying and the other 2 like to make the thrust to move one direction. Something like that, or
to accomplish the holonomic flight that I described, the 6 motors have to be tilted or reconfigured.
Okay.
If we require perhaps to increase the flight endurance, then we can make it make all the motors parallel and all upwards. So we get something like what you got here.
Is there any question? No. One more.
Okay.
With the optimization problem, can you put the constraints? You say you want to maximize. Yeah, exactly. So this is, or you put the first one, I think, is the close force satisfaction or constraint.
The first?
Yes.
This one is the equilibrium.
The equilibrium.
Given a coefficient for all forces and the graph matrix, the product has to be 0, so the wrench around the body is 0.
You are trying to optimize a dynamic system, so that when it is flying, you have some dynamic effects on the body, inertial effects, gravity effects, and so on. So because it is a dynamic system, when you try to maximize it, I think you have to consider also the dynamics of the system as a constraint to be satisfied. Otherwise, it's like you may find a D, so that satisfies these constraints, but not necessarily the dynamics equation.
I
consider like that.
We consider the graph matrix just to test the static performance.
So it's more like you are doing a static.
Yeah, because during flight, the configuration of the vehicle is not changed. it's always maintaining the 40 degrees in the well. On the other hand, on the flight simulation, yes, we use the dynamics, the rotational.
Okay, the dynamics. Okay, yeah, wow. Well, on behalf of the organizing committee, we thank Daniel Soto, and we give them a recognition for his participation and his participation.
Thank you very much.
Well, now we welcome once more Daniel, because he is the presentator of the next talk. This talk has to do again with the Hexapod, I think.
Yeah, that's right.
And now the title of the talk is H3P, a walking gate generator algorithm. You have a session for yourself.
So, yes, because we had the idea of building this robot, the Hexapodopter. We also have worked before with standard multicopters. Standard multicopters have a very easy way to work with. You create a mission plan, you upload the mission plan to the vehicle, and then during flight you can switch to auto mode, and you can make it describe this mission plan automatically. And because it is on the air, you don't have to care about well, you have to prepare. Well, because it is on the air, it can move freely on the air without taking too much care about obstacles, right? So we tried to use this idea to create an algorithm that could help us make the example over land, describing a flight plan. Well, no, this time land plan, a mission plan for the land. Yeah. So, like locomotion is the ability of an agent to move from one place to another in a controlled manner. This has to do also with the stability of the past algorithm I showed you. For example, the snakes, because they is linear over land, they are very stable. The most part of their bodies are touching the ground, so they don't care about falling. On the other hand, like animals, use cyclic coordinated motions of their limbs to propel themselves forward. The gate cycle is divided into two phases, support and swing. This means that because we have to link the two legs, one leg is supporting our weight, and the other leg is swinging further ahead of our center of mass. That's right. That's the two phases described. And there are also other approaches to create this locomotion pattern. There are mathematical approaches where the gate cycle are fixed. So the end result is a static pattern that can be repeated when moving forward ahead or turning to one side. There are like the two basic randomers. And there are also the virtual model approaches where they forget about the complexity of the leg, and they create they instead use a spring or damper to describe how our leg performs. And there are also vice-pair approaches based on heuristics that emulate the motion of robots. And this, perhaps you have heard about cyclic generators, CPGs. I don't remember what it is for. CPG? Gate. Okay. Okay. And this, well, they use a cyclic signal, and they change the amplitude and the phases and the frequency to create a walking pattern. depending on the input, they generate a cyclic output, and this cyclic output is mapped to the motion of the link. Right? So instead of this, the algorithm we propose is a kinematic planner for the robot that dynamically generates the gate pattern to make the robot follow an arbitrary trajectory at an arbitrary speed. That means that given a mission plan, as I described in the beginning, we can describe a trajectory, an arbitrary trajectory, and also make the robot walk over this trajectory at the velocity we want, always maintaining an static equilibrium. So again, we use the same model. This time, each link was grouped in two different subsets, which define a tripod for the structure, and the odd legs and even legs were grouped in two separate subsets of legs, each defining a support polygon, which is a triangle for the robot to walk. To each of the subsets, we attach a reference frame that defines the position of the given leg and the off leg with respect to the center of mass. By changing each of the positions with respect to the center of mass, we make the link, the subsets change its position with the center of mass just by changing this convention. Right? So we use the standard dynamic Hartman parameters to describe the configuration of each link. Here I show you the degree of freedom, the lead, and the mean degree of freedom. The tree define the configuration of the link at all times, right? So, given this kinematic analysis, KTP is a kinematic planner that dynamically defines the grid pattern for a robot given a velocity command. You see a vector under a static condition of the equilibrium. So for the support tripod and the swing tripod, we have to define, to propel the center of mass forward given the velocity vector. How can we do this? Is by first defining where the center of mass should be, and then reconfigure the support tripod. And also the swing tripod, because the robot may move to one side or straight ahead or to the right. We have to make the swing tripod move on each direction, on the direction of movement we plan to move to, or defined by BT. And also the phase shifts. When the two tripods can or should switch between the support or swing phase of the cycle. So when we walk with this leg in front of us, shifts to the support cycle, and this, which was performing the support, moves to the swing, and this is performing cyclically. So we get the gate pattern, right? All these questions were analyzed and solved. The first, how to make the tripod move, how to make the center of mass move in the desired direction, was defined in a vector. As you can see, we included the phase, the position and pose of the vehicle and their corresponding changes, rates of change, the derivatives. So given this and the velocity vector and the velocity command, the desired center of mass adds an integration from the initial state. That's previously how the velocity components are multiplied by delta t, so we get a delta x. displacement, small displacement, and it is integrated with the current state of the vehicle. So given this desired position for the center of mass, we then use a PV controller to propel the body of the robot forward. And to support this movement, the support tripod has to be reconfigured so that we get a slip-free motion. That means that if the center of mass will move in the direction given by the input command, and all legs, limbs supporting the body of the vehicle should be reconfigured accordingly. So we define a constraint. As an example, here I show you a rigid body transformation. So what this means is that with respect to the world reference frame, the rigid body transformation from the tripod supporting the body of the vehicle has to remain equal. That means that when I propel the center of mass of the robot, the support tripod remains fixed to the world reference frame. So we solve this constraint, and using this constraint, we define how to make the robot move forward and the support tripod remain stationary with respect to the world reference frame. Right? And for the tripod on the swing face, we define two different cases. The first one, when the robot is moving straight ahead, so we are working straight ahead. The desired position for the swing tripod is just straight ahead over the center of mass. And on the case where the robot is turning, how far it goes to each side, to the right or to the left, is defined by the turning radius, by the instantaneous turning radius of the vehicle at the moment we receive the velocity command. Right? And how far the swing tripod will move ahead of us is defined by the height, the clearance of the robot at each moment, and the theoretical maximum extension that the robot can cover at one step. So this distance that I showed you, Lmax, we made it the 70% of this maximum gate distance. So that means that I have some work range to walk, and also to extend a little more or a little less. It depends on how we will perform the gate cycle. Right? So that's how we define the desired position for the tripod stringing ahead of the robot. And then once we define the support and the tripod swinging ahead of the center of mass, we just do a joint reconfiguration using the inverse kinematics problem for an RRR link. From this, we get the desired orientation for each of these joints. And given that, we just execute the change in orientation of each joint, and we get the gate pattern that I showed you. For the last thing we have to care about is how we change the phases. For that, we define 3 tests that make possible for us to keep an static equilibrium and also make sure that the legs don't collide with each other. The first test is that the maximum length of the step has to be equal to Lmax, which you might remember from the past slide. So if we move the link further ahead and this link is already ahead of us, Lmax meter, then we trigger the T1 test, and a phase shift occurs. And the other is when the robot is turning, it may two limbs may get too close to each other. Get too close to each other, I will show you this angle. If they get too close to each other, then a phase shift is triggered so that the swing tripod lands, and the swing and the other tripod supporting the vehicle can take up and move to continue the turning motion of the vehicle. And lastly, the third test is to make sure that the joints are working in predefined work range. If by any chance the limbs are working outside of the workspace, which is a very common test in robotics, then the K3T3 is triggered and we perform a phase shift. So given this algorithm, this overall description of the robot, we used also the learning feature, the velocity command at each moment in time. As you can see here, I showed you the magnitude is given by a simulation parameter, and the direction over the learning trajectory is just given by the derivative of the learning trajectory. So given this input command and the parameters here I show you, the gain for the controller, the parameters for the learning state, the initial position for the robot, the working range for each joint, the lift, the knee, how long it was the maximum gate distance per max, and the dimensions of each section of the robot. So given these parameters and the algorithm I just showed you, we made this simulation. Here I show you how the robot walked from the beginning, from its initial position, along the length trajectory, dynamically walking over the irregularity uneven terrain. This area is completely level. And the second plane is slightly tilted. It has a certain inclination, right? And here here I show you when the phase shift was triggered. The two tripods touch the ground, so the tripod on the behind the robot begins to take off. Here I show on these situations. Here I show you several situations in which the center of mass also always remains on the intersection of the two areas. So it is stationary even during the phase shift. And this is a simple graph showing how at the beginning the shaded area corresponds to the even leg swinging. So only on this period of time the even legs were swinging, and here we can see that the phase shift was triggered by the minimum angle between two legs. And on this, the first test is the second to be triggered when the maximum distance here in the blue plot goes away, goes further ahead from the threshold we defined. This is just the transient response. At the beginning, the robot aligns with the P and the XY axis. You can see how the two are getting too close to each other. It has to be some error to track this trajectory. So it's always almost overlapping, but not touching each other. The error stays close to zero. That's it. Just I show you the control command of synchronous, and this is the cyclic control transients for the walking pattern. You can see that that each time the phase shift is triggered, the control command for the swing tripod increases in magnitude, and then decreases when it almost reaches the desired position, and then a phase shift occurs, and this cycle pattern repeats itself. So as conclusions and future work, K3P is proposed as a novel approach for dynamical gate generation for extracted robots. The new algorithm is based on a kinematic planner for the less organized as tripods, the support and swing tripods, so the even tripods. At the core of K3P are the three shape-based conditions, the K3P 1 to 3, that ensure the static stability of the robot throughout its operation. K3P does not require any pre-computed information for the trajectory to be followed, nor the trajectory for every support. So all the trajectories are computed in real time, or as the velocity command is received. The gate pattern is dynamically generated, taking into consideration the physical dimensions of the robot, avoiding collisions between legs, and maintaining unstable gate at all times. That's it. Thank you for your attention.
Well, we thank Ani. We have time for some questions. Is there any question? No question?
Am I crazy?
Well, I helped you. Okay. That's not the job of the chairman. Okay. There are no questions from audience. If I wonder, because you say and you show that you design all the trajectory, the path generation, the gate generation, based on kinematic issues. Furthermore, the robot, because it has the triangles that are shifting all the time, and the mass center is always on this supporting area. So how is it by itself stable on the working? Oh, yeah. And then, sorry, you mentioned that this is a dynamic gate generation, but I don't see where the dynamics is getting into. I mean, you are not like working out the torques on each motor. It's more like you are generating actually the velocity profiles on each one of the legs. So where is the dynamic really getting involved?
I will begin by saying that this velocity command was generated during simulation. So given this velocity command, as I described, the center of mass is propelled forward. From this forward movement, the support tripod is reconfigured to make it move in the desired direction and perform a slip-free motion. And from this new position, the desired location for the tripod changing is defined also dynamically. So what I mean from dynamically is that given the velocity command, is the position of all the tripods are computed dynamically at each iteration step.
What happens if you correlate these ideas with the biped robot? Okay. Legs robot. When it moves slowly, it's enough to consider the mass center location to be over the supporting area. Yeah. Okay. So if that's static working. That's static working. When you move fast, then this static criteria is not good enough. Then Guerrero show that you have to consider this zero moment point. That's right. So it means to take into account the inertial effects of moving with certain velocity and acceleration, or not really, just as you say, if you walk slowly, it's no problem, but if you go faster, that's the difference between a static criteria and dynamic criteria. That's right. So in this case, is that you're working with mass center location at each time you are shifting the angle. That's why I say I don't see really where dynamic effects on the generation of the path.
Well, I really want to get this point across. Yeah, the center of mass is moving in the commanded direction. The gate pattern, the position of each link, each tripod is defined at each iteration step. So that's what I mean when I say that the gate pattern is generated dynamically. Just and the equilibrium condition is only a step. That's not on that way.
That's another question. And we thank Daniel for the presentation. Thank you very much. Thank you for being here. I have no problem to show your work. Thank you very much. Well, this briefing is the first session of Mechatronics, this international conference on electrical engineering, computing, science, and automatic control. And then we will have a coffee break, half an hour, and then we will have our inauguration. Thank you very much.
Oh, yeah.
¿Tienes el apuntador?
Ah, sí,
¿Te lo usaste? Sí, a las 10:30. Ya hay café, algunos bocadillos, si gustan pasar. Oye, perdón, por ahí no pude ver, ¿de dónde nos visitas?
Ah, de San Tamaulipas.
Ah, Tamaulipas. Sí. Ah, ok, la parte de Computing Science.
Exactamente. Pero bueno, allá con el profesor somos los que estamos haciendo trabajando con este tipo de cosas y somos los de los pocos. ¿Tal vez conozca al doctor David?
Sí.
Ah. Sí, es el único interesado en este tipo de cosas.
Sí, para la simulación lo hacen en MATLAB.
Claro, MATLAB. Los trabajos prácticos ya los tratamos de mover a Linux. Ajá. Pero sí, la simulación ha sido más lo del caballito de batalla.
¿Ya han visto algún prototipo?
¿Lo trabajan? Pues sí, hemos tenido. Ahora que es una estancia allá en Japón. Pues sí, tiene trabajo también y algunos comentarios que ustedes saben. Todavía no lo tenemos, pero sí están. Sí. ¿Sabes en el proceso? Sí.
Ajá.
Entonces, presentamos antes de que iniciara oficialmente.
Sí, primero hubo una sesión de las 3 áreas.
Ok.
Y ya ahorita va a ser la inauguración oficial.
Okay.
Sí, además,
yo creo que voy a tratar de hablar.
Ah, sí, por eso no. Ya después vino Valencia y ya se había conectado. Pero que estaba mal, porque ya no tenía el agua ahí. ¿Entró entonces? Finalmente se conectó porque estaba mal. Bueno, Valencia lo chica y ya le mandó las transparencias. Lo regreso. Sí, sí.